today we talked more about the relationship of simple harmonic motion and uniform circular motion. So we talked about how, and it's easy to think about how when you have a spring, so moving on a spring, it goes back and forth like this in a very regular pattern, where it goes to some maximum amplitude A, to some minimum amplitude negative A, going to the equilibrium point in between. So if we have something moving in a circle, say like this, okay, it is exhibiting periodic motion also. And if we tip it on its side, you can imagine this by looking at this, tip this on its side, it is doing the same sort of thing. It has a maximum that it reaches, it goes through a middle equilibrium point, goes to a minimum amplitude, the negative A, over there again, where A is going to be the radius of this circle. Okay, and so it is exactly analogous for these cases. It goes, if you were to flatten this into one dimension instead of these two, it's going back and forth like this. So if you were looking at this completely edge-on without being able to see the fact that it's moving around in the circle, all you would see is the position of this moving back and forth across the field of view with the same sort of behavior as that of something on a spring. Okay? And so, if we're looking at this from the side, the object hanging off the end of this circle will be over here, circling around, going back, circling around, going back. So we'll have that periodic relationship, and you can express the speed, this is going around in the circle, as the distance is going over one time for a period. So that speed would be 2 pi times A divided by the period. Okay. Now if we're looking at a spring, and we're looking at an object moving all the way over here, if we stretch it out at some amplitude A, and we'll go back over here to negative A, to A, and back again. And we know that as we're watching this happen, that you have the potential energy that's stored in the spring that you stretch it out with the start, all gets converted into kinetic energy at one point when the potential energy for the spring drops to 0 at the equilibrium point, and then back into potential. So when you first pull it out, if this is x equals 0, and this is x equals A, you pull it to A and let it go, it's going to go through 0, so it'll be about here, and traveling back this way, then it will go to negative A, and then it will go back to 0, etc., and it'll go back to A. Okay? So at this point, when you let it go, it has no kinetic energy. Then, as it passes here, when it reaches the point where the spring is not stretched or compressed, it's going to all go into kinetic energy, and then we'll go back into potential. And so the maximum kinetic energy, or the maximum potential energy, first of all, when that A squared, is equal to the maximum kinetic energy there at the center. And this V at the center is going to correspond to this V here. And we can think about that because if we look at this, and we think about this as flattened, we can actually look at this as just the velocity in the x direction. So the part that's going this way, as opposed to the part that's coming out in the y direction. And at the equilibrium point here, at x equals 0, that speed is going to be a maximum for the x direction in the velocity. Okay? It's not going to be moving back or forth in the y, it's going to be moving all in the x. So in that case, those v's are going to be equal. And what that means is that we can set these two things equal to each other to get a relationship for the period. So this, the halves cancel, you have a squared over v squared is equal to m over k, or that a over v is equal to the square root of m over k. And there's an a over v right here, if you rearrange things. So you can see that the period, t, is equal to 2 pi the square root of m over k. Okay. So the period of simple harmonic motion can be related just by the mass of whatever object is on your spring, okay, and the spring constant there. No other quantities need to be involved. You can tell the period of this oscillation just by knowing the mass you attach to your spring and the spring constant. Okay, now this brings in something else that we need to talk about, that we know that t is equal to 1 over the frequency, because they're reciprocals of each other. So that means that t is equal to 1 over this, or t is equal to 1 over 2 pi, the frequency is 1 over the period. And so the frequency is going to be equal to 1 over 2 pi, the square root of k over m. But we also know that we can relate this to the angular frequency, where omega is equal to 2 pi times f. And so f is equal to omega over 2 pi, which means that omega, the angular frequency, is equal to the square root of k over m. Okay. So that's the angular frequency, or also actually the angular speed of this thing moving in a circle. And we're going to use that right now to actually talk about expressing the position of this object moving in a circle in terms of its angular frequency. So let's look at this from above. So now this object is moving in a circle, and like I said, we're going to look at the x component of the velocity as it's going around. Let's say it's going to go clockwise like we had it going in class. Center is more about there. And so if it starts over here, then its x component for position is at minus a. Okay. Now as it moves up, it's now going to have a new x component. The radius is still the same, the radius is still a. It has a new x component that's shorter. The y component, however, is bigger, because the y component over here was 0. Now, as it goes all the way over to here, the x component is now 0. And then as it goes over here, the x component will get bigger again until it reaches a maximum over here. So it goes, the x part goes back and forth between the maximum of a and 0, and the minimum of a as it goes around the circle. Okay, and so we can express that in terms of angles, the angle from the x-axis, like we have been doing in other parts of the course last semester. We have, say it's here, okay, this radius is a, we want to know its x position right here, and so in order to find that, we need to know this angle here, and therefore we can say that x is equal to a times cosine of theta. Okay, just by using trig, because the cosine of theta is the adjacent side over the hypotenuse. And so to solve for the adjacent side, we should multiply that, the a over to this side, so we get the position at any point in the circle is equal to the radius times the cosine of the angle right there. Now, if this object is exhibiting uniform circular motion, that means that its speed is constant going around the circle, which means that we can relate omega by theta over t. It's the angular displacement over a given time period. Okay? So that means that then we can put in theta is equal to omega t. So x is actually equal to a cosine of omega t. So at any given time in this situation, as long as we know the speed at which this is going around the circle, we know what its position is. And then we can also figure out, based on some other things, that v, the speed at which it's going around the circle, is equal to minus a times omega times the sine of omega t. Okay? And then a, the acceleration is experiencing going around the circle, is minus a omega squared times the cosine of omega t. And if you wanted to work in terms of frequency instead of angular frequency, you can just put omega equals 2 pi f into each one of these arguments for the trig function, and you can solve it that way. But these relationships tell us that if we know the angular speed, and we know the radius of the circle, then we can know exactly at any given time what its x position is, what its velocity is, and what its acceleration is. Okay, which is an important thing to know, and it lets us, relate this more for the simple harmonic motion case. Okay? Because cosine and sine are periodically varying functions, which goes along with the idea of this periodic simple harmonic motion.